Okay, so I think it's time we may start. As I said, I cannot announce new seminar now, so we have about 2 or 3 weeks vacation, and please suggest any speakers and topics of seminar, and we will organize it at the end of August or at the beginning of September. And now we have a last seminar in this season. Our speaker is Sergey Vyatchanin, who is both the member of our Quantum Technology Center and the Scientific LIGO collaboration, and he will talk us about quantum correlations between light and the kilogram mass mirrors of LIGO. Please.
Thank you very much. Please excuse me for problem last week. Now the technique is more wise than we, and we should overcome these difficulties. My topic is about literature. In July in Nature, there was published the paper which was titled on the slide, and I would like to explain what authors means. First of all, I will start from simplest position meter. I recall that gravitational wave detector, practically it is a very good with very high precision position meters. And we consider this simplest example to clarify the situation. That we have free mass, and it is test mass, and we measure its position by phase of reflected wave. It is test mass is a mirror. From point of quantum mechanics, in the reflected wave is in the position is entangled between each other, or it can be called as quantum correlation. If we have incident wave to be in coherent state, then we have the mean amplitude and the vacuum fluctuation around it. It is on plot on figure on the right. It is shown by blue circle. After reflection, due to the ponderomotive pressure acting on mirror, this fluctuational circle will became the ellipse, which means squeezing. During this squeezing, we see that amplitude quadrature conserved, and phase quadrature disturbs. It is can be explained by this equation 1 and 2 for amplitude quadrature and phase quadrature. Here, coefficient k is a normalized. It's a power number, normalized power, and we can recalculate output phase quadrature as equation 3. We see that we have the fluctuations, the force, small fs is force normalized to standard quantum limit, and two terms. We can easily calculate the spectral density power spectral density recalculated to in terms of Fs, it is equation 5, and the plot is present. A plot of this power spectral density is presented on the right. We see that on frequency omega 0, it has minimum. In larger frequency, the blue curve, it is increase of spectral density is due to coefficient K became smaller, and blue term in 3 is working, and the degradation of sensitivity at smaller frequency explained by increasing of backaction noise. It is presented by red term on equation 3, and in this case the polymorphic degradation, polymorphic backaction became larger. If we have some squeezed light, for example, by phase, as on slide here, we see that we have practically the same equation, but spectral density of amplitude and phase quadrature are different. And here we see that just sensitivity curve, spectral density SF, just shifted on the right. If we have amplitude squeezed pump, then we have opposite situation. The sensitivity curve shift on the left. It concerned of constant amplitude squeezing and constant phase squeezing. We can imagine frequency dependent squeezing. For example, we can assume that at frequency smaller than omega 0, we have amplitude squeezing, and for frequency larger than omega 0, we have pure phase squeezing. Then sensitivity curve will be presented in the bottom of slide, and we see that the bandwidth of detection will increases. We can use variational measurement. If we have a strong pump, the reflected light will be squeezed, as shown on the left, by red ellipses. And but in order to have increase of sensitivity, we have not to measure amplitude or phase quadrature, but it's combination. Indeed, a balanced Hamadan detector measures arbitrary quadrature, as following in equation 18. So if we substitute amplitude and phase quadrature into this equation, we can see equation 19, and we see that blue term here, it is can be compensated, maybe equal to 0, at least at one spectral density. And so at one frequency, we can completely compensate backaction. In that case, overcome standard quantum limit. And this, it is the plots shown here. We see that sensitivity curves can be slower, lower than one. One, it is a standard quantum limit, and we can surpass SQL. We would like to underline that for reflected wave, squeezing will depend on frequency. For smaller frequency, omega less than omega 0, squeezing is larger than squeezing for frequency larger than omega 0. It explains when we can have not complete compensation of backaction, but only compensation in some bandwidth. Let's understand what we can do if we have squeezing of input is in input light, but squeezing not amplitude or phase, but some arbitrary squeezing, which we can suit so that this squeezing is shown by blue on the left. We can choose orientation of these ellipses that for reflected wave it became pure phase squeezing, as shown on by red ellipse. Of course, it is on some spectral density. So we can surpass standard quantum limit. Practically, this case is discussed by authors of this paper. We first of all we formulate our review result for simplest meter of free mass mirror, and it can be recalculated for case of Fabry-Perot cavity if we have fixed input mirror and movable end mirror. In this case, we can show that formulas for input-output relation will be practically the same, but the formula for power parameter K will be more complicated. But the physics will be the same. Now, now we can go to interferometer of LIGO. It is shown on this slide. It is interferometer Michelson with Fabry-Perot cavity in arms, and for this interferometer, if we are interested in difference mode. In this interferometer, there is symmetric mode and difference mode. Symmetric mode is pumped by laser, shown here. Let's imagine that all these mirror are fixed, except end mirror in north arm and east arm. if and we tuned this interferometer so that laser goes into cavities, bounce inside it, and then go out to the same vein. No light goes to the signal receiving cavity. In ideal case, of course. If the end mirror will be shifted symmetric one, for example, nose mirror and east mirror goes outside on the same shift, then situation will not change. In any case, all light will return to laser port. If we have the situation when is interesting for gravitational wave detector, when, for example, nose mirror shift outside and east mirror shift inside, it is the case of action of gravitational wave on this interferometer. Then appears the signal in signal port, and it is provide information on gravitational wave detector. It can be shown that this interferometer can be reduced to Fabry-Perot cavity, but only in this Fabry-Perot cavity in our arms, we will have pump from the laser and noise from this duct port. Only noise from duct port will be define the noise masking the gravitational signal. In this case, we see that this interferometer is similar like Fabry-Perot cavity, and Fabry-Perot cavity is similar to single mirror, which we consider above. In usual case, the noise from duct port, it is vacuum fluctuations. But if you want to use squeezing of input on this language as in input line, we should squeeze vacuum here and inject into interferometer, and then it will go output and will register by homodynamic detector. So the physically all consideration which we present for simplest position meter can be applied to this interferometer of LIGO. Now,
excuse me, may I ask a short question about setup? Does the squeezer pumped by the output signal from laser, or it have another pump?
No, in this case, the laser and its noise goes into the interferometer and go out through power recycling mirror output.
Mm-hmm.
And the signal which provide the information on gravitational wave signal is contain noise which goes from DAC port, from signal port. And laser should create only large mean field in arms. I answer, not?
Okay, thank you.
Now there is sensitivity of LIGO is going towards standard quantum limit, but main factors restricted sensitivity now. It is a thermal noise of in material of mirror. It is thermal fluctuation in coating of mirror and in body of test mass or in substrate test mass. The list of factors which contribute noises is very long, and this is only on the main. And now the sensitivity of work in bandwidth between 50 300 Hertz defined mainly by thermal noise. And this noise is larger than quantum noise by several times. Sensitivity on frequency larger than 300 is described practically by quantum shot noise. So the main result of this paper I review is the following. The author inject into interferometer squeezed light with constant angle and they looking what will be. Here, let's consider these graphs slowly. First of all, this line, red dotted line, describe the standard quantum limit. Blue line here described the sensitivity which would be if only quantum noise present, no others. It's theoretical curve. The main experimental course is a gray. It is a total noise if we with unsqueezed vacuum noise. When in DAC port we do nothing to squeeze. Just it means that to DAC port the vacuum noise injected, and brown is correspond if we squeeze input light by 3 dB, and we see these curves. Practically, from these two experimental curves, authors make rather strong decision. They try to first of all they plot the magenta curves which should be for squeezed noise input if no thermal noise present. So they took this sensitivity brown and gray, and they tried to subtract thermal noise, and the result is this green line, and they after this they call that they are great, and because we see that this red line goes below standard quantum limit, and we can proclaim that we overcome standard quantum limit. In the bottom of these plots, we see the squeezing of input light of this dotted, it is input squeezing, and blue magenta is output, which should be if we have no additional technical noise. I understand. I repeat that the squeezing angle is a constant here. The next step will be usage of frequency-dependent squeezing. Now it is for constant squeezing. Authors also show the plots for different value of squeezing, of angle of squeezing. Value of squeezing is the same. It's 7 degree, 24 degree, and 46 degree. And in 24 and 46, we see that subtracted noise is below standard quantum limit. It is the main result, and the result formulated in article formulated is presented here. The observed radiation pressure noise is also demonstrated that observed radiation pressure noise contribute large contribution, into of quantum vacuum fluctuation can influence the motion of macroscopic object. We see that if in this case we see that quantum noise of light define the movement of macroscopic 40 kilogram mirrors of LIGO. It is the main some result, but it is with some it's some recalculation. It's not direct experiment. It's result of the calculation of real experiment. If so, they can proclaim that they demonstrate surpassing of SQL in Advanced LIGO interferometer for the first time, and with back action evasion technique. And also hope that this squeezing activity will allow to increase the sensitivity of gravitational wave detectors now, and it will give the possibility to register to register some events by gravitational detector more often than now. They hope that it will increase. Thank you very much.
Thank you so much. So please ask any questions about, I think, about both this work and current work of LIGO. I think you may answer yes. Okay, Paulo, please.
Thank you. So very interesting subject and a very nice presentation. So is it correct to understand that they did not actually surpass the standard quantum limit because they subtracted the technical noise? Is it correct to understand that?
My task is review the result of paper. There is two opinions. First, we see that quantum noise is below standard quantum limit, and pessimist can say that I do not see it because it is just recalculation of experiment which do not demonstrate it. But the majority of society is assume the first point of view, but it's your choice.
Okay, I have another question. Is in the conclusions, the first statement is that the vacuum fluctuations are affecting the motion of the mirror.
Yes.
How can I see this? Because I understand that. I don't see this. How the light is changing the motion of the mirror. I see that the light is detected.
Yes, but if you believe that green curve is a real curve, not recalculated, not very qualified, and you believe it, then you see that in this green, in this region, you see there is surpassing standard quantum limit. It is with the same the result with the same words of possible criticism. Yes, I agree.
And just a last, maybe a comment or a question. I'd like to know your opinion about this. So the light is being used to measure the displacement of the mirror. Then it is a classical pointer in the sense that you only need a classical correlation between the light and the position of the mirror. Do you agree with that? Because I mean, it's just just the quadrature position of the mirror that is being measured. This is a pointer basis. I mean. So then it's a classical correlation between light and the mass position.
Yes, it's if you it's classical correlation, but if you people say that if you have sensitivity larger than standard quantum limit, it is classical words. If you have demonstrate surpassing of standard quantum limit, you go into quantum world. That's
okay. So thank you very much.
Any other questions? Okay, I have a question. As I see now, so there were a set of upgrades of LIGO. So first of all, they used just coherent light. Now they use squeezing at dark port. But will they use squeezed light at the input port?
The next generation of LIGO, Voyager, it will be larger laser and shift of its frequency into red region. Now it's discussed. It will be 4 or 2 microns. And next step, next feature is now all test mass are fabricated from fused silica. It will be fabricated from silicon. Maybe this mirror of in arms will be freezed. It's planned to be at temperature 123 Kelvin. It's a plan for future, for next generation of LIGO.
Okay, thank you. And one more question. When they start to use this squeezing and its output, did they register any gravitational wave with this squeezing?
No. It's demonstration. It was only demonstration.
Okay.
Because usage of this regime in routine observation is very difficult. It's just experiment. Excuse me.
Okay, I see. Thank you. Konstantin Kravtsov, please.
I have a question about the model that you use here. So you always assume that one of the masses is free moving, right? So is that necessary? Is that necessary for detecting gravitational wave, or is just the model that you use for explaining those quantum things?
Yes, practically, of course, all these mirror are hanged by on fibers, and pendulum mode is about 5 Hertz. So in this regime, it can be considered as free mass. Free mass is good from that point that the bandwidth of working bandwidth will be rather large. There is a variant of gravitational wave detectors, resonant. It can have similar, maybe better sensitivity, but in resonance, into mechanical resonance, it means in very narrow bandwidth. And here all efforts are aimed to have detector which working in bandwidth 50 Hertz to 1000.
I see. And maybe one more question. Is it good that the mirrors are that heavy, or is it better to have to have a lighter mirror or a heavier mirror? So because it somehow changes the numbers in your theory that you showed.
Yes, the increase of mass mirror, you mean?
Yeah. What
yes,
is
yes,
the best?
yes.
Have a heavy mirror or light mirror?
the plans is increase of mass of mirror till 200 kilogram.
And that will improve the sensitivity, right? With all those quantum.
You see that increase of mass doesn't increase gravitational signal, but it can decrease technical noise.
Okay.
It's the reason.
But the equations that you showed, there are the mass as a parameter of all those. Well, as far as I understood, there is mass in all the equations. So if you change the masses, then you will change some coefficients in your sensitivity equations. No?
Yes, and then for larger masses to go to reach SQL sensitivity is became more difficult task. Yeah, I understand it. But
okay.
But main aim is gravitational wave detection.
Mm-hmm. All right, thank you.
But this situation that this macroscopic detector, 4 kilometers, 40 kilograms mere test mass, goes to standard quantum limit sensitivity is very impressive. It's not reach SQL or reach as authors proclaimed, but in any case, it's fantastic. You see that you observed quantum behavior of 40 kilogram mirror.
Yeah, it's impressive. So we have traditional question from Ranjit, please.
Thank you. Thank you for the talk. I have two questions. So in your presentation, I have seen equations, I think 1-5. Are these equations are obtained by solving Heisenberg equations? If yes, then what is the form of direction Hamiltonian?
Yes, it's practically it's practically Heisenberg equations, and for example, this one and here all operator are it's a Fourier transform.
Mm-hmm.
Yes, you are right.
Okay, so the second question is, can we apply polarization squeeze light concept in the LIGO interferometer and study polarization noise fluctuations? Will polarization concept bring any benefit?
In LIGO, the polarized light is used in order to control all measurement. About effectiveness, how effectively this control, I don't know. I cannot answer it.
Mm-hmm. Thank you.
Okay, we have a question in our chat. So Rene Araujo asks, what does ponderomotive mean?
Ponderomotive, it means light pressure, light pressure force. It is ponderomotive means that light acts with mechanical force on test mass.
Okay. Any other questions? Okay, if that's all, so thank you again for the talk. It's a very interesting talk and a very interesting topic. Thank you. And as I said, I don't know when will be the next seminar, maybe 2 weeks or 3 weeks later. So watching for announcements, and see you at the end of August or at the beginning of September.
Yeah.
Thank you.
3 weeks we can play like children.
Yes.
Okay.
See you.
Bye-bye.
Bye-bye.
See you.